In this video, we'll talk about two applications of the result that we just proved. And this first one is Corollary 22 in section 14.4. It says that if K1 and K2 are Galois extensions of F and their intersection is F, then the Galois group of K1, K2, the composite over F, is isomorphic to the direct product of the Galois groups, the Galois group of K1 over F cross the Galois group of K2 over F. More than that, there's a converse that's true, that if K is Galois over F and the Galois group G of K over F is the direct product of G1 and G2, so it's the internal direct product of two of its subgroups, then K is the composite of two Galois extensions, K1 and K2 of F, with K1 intersect K2 equal F. Okay, so the first part of this follows very directly from the proposition we just proved. We know that the Galois group of the composite over F is isomorphic to the subgroup of the direct product consisting of all pairs, sigma in here, tau in here, such that you restrict sigma to K1 intersect K2, you restrict tau to K1 intersect K2, and you get the same automorphism. But if K1 intersect K2 is just F, every sigma in Galois K1 over F fixes F. Every tau in Galois K2 over F fixes F. So it's just always true that sigma restricted to K1 intersect K2 is equal to tau restricted to K1 intersect K2. So that's what I've written here. Every sigma in this Galois group, tau in this Galois group satisfy that their restrictions to the intersection K1 intersects K2 are the same map because it is the identity on F. Okay, so now let's prove this converse direction, which is more interesting. Let's name, so we're handed a Galois extension and we're handed two special subgroups of the Galois group. So given a subgroup of the Galois group, you have a subfield of K containing F. So let's name those fixed fields. Let's let K1 be the fixed field of this subgroup G1. So K1 is the subfield of K consisting of everything fixed by G1. And K2 is the fixed field of G2. Okay, so the fundamental theorem of Galois theory tells us if we have K1 and K2, these intermediate fields, we know the subgroup of the Galois group corresponding to K1 intersects K2. So what is it? By the fundamental theorem, K1 intersects K2 corresponds to the subgroup of G generated by G1 and G2, the smallest subgroup of G that contains G1 and contains G2. But that's equal to all of G because every element of G is of the form something in G1 times something in G2. Why? Because G is a direct product of G1 and G2. So everything in G is something in G1 times something in G2. Okay, so what does that mean? K1 intersect K2 corresponds to G, the whole Galois group, under the Galois correspondence. But we already know what field corresponds to the entire Galois group under the Galois correspondence. It's just F. So K1 intersect K2 has to be F. Okay, let's apply the fundamental theorem again, but this time to determine the subgroup corresponding to the composite K1, K2. Okay, so what is that? We know that the subgroup corresponding to a composite of two of these intermediate fields is the intersection of the corresponding subgroups. So we see that the subgroup corresponding to this composite is G1 intersect G2. But what is G1 intersect G2? What does it mean for G to be the internal direct product of G1 and G2? It means everything in G can be written as something in G1 times something in G2 in a unique way. And that means that G1 intersect G2 must be the trivial subgroup. This is part of what it means to be the internal direct product of two subgroups. So G1 intersect G2 is trivial. So what does that mean? The subgroup corresponding to this composite field K1, K2 is the trivial subgroup. But we already know which subfield of K corresponds to the trivial subgroup under the Galois correspondence. It is all of K. So since K1, K2 corresponds to the trivial subgroup, we see that K1, K2 is all of K. So what have we seen? K is the composite of two Galois extensions, K1 and K2 of F, with K1 intersect K2 equal F. Next, we'll state and prove Corollary 23, which is one of the most important results of this section. Let E over F be any finite separable extension, not necessarily Galois. Well, E isn't a Galois extension of F, but it's contained in a nice minimal Galois extension of F. So what we're going to prove is that E is contained in an extension K that is Galois over F and is minimal in the sense that in a fixed algebraic closure of K, any other Galois extension of F containing E contains K. So the way to think about it, this inside a fixed algebraic closure, like you might have different algebraic closures where you have different splitting fields, but they're all isomorphic to each other. So in a fixed algebraic closure, you have all these Galois extensions of F containing E, and one of them is minimal in the sense that any of the other Galois extensions of F containing E have to contain this minimal one. Okay, this extension, this minimal Galois extension of F containing E gets a name. This Galois extension K of F containing E, this should say containing E, I'll fix it. Containing E is called the Galois closure of E over F. So what's one big idea in Galois theory is that we've been able to study extensions that are Galois by looking at the Galois group, that's some finite group, and looking at the correspondence between subgroups of the Galois group and intermediate field extensions. When you have an extension E over F that's not Galois, you just can't do that. But you can instead take the Galois closure, and then you can look at the correspondence between subgroups of the Galois group of the Galois closure and subfields of the Galois closure containing F. And this field, E, is going to occur somewhere in that correspondence. Okay, so let's think about some examples that we've talked about involving extensions that are not Galois, finite separable extensions that are not Galois. Q adjoin the cube root of 2 is not a Galois extension of Q. What is the Galois closure? Well, it's contained in this extension Q adjoin cube root of 2 and zeta of 3, which is Galois over Q. We know that there can't be any other field in between these two just for degree reasons. This field has degree 3 over Q. This field has degree 6 over Q. So there's no smaller field than this one that could be Galois over Q and contain Q adjoin square root of 3. Okay, the Galois closure of Q adjoin the fourth root of 2, same kind of issue as this one, is, well, this extension is not Galois. If you take the extension Q adjoin the fourth root of 2 and I, that is a Galois extension of Q. It's the splitting field of x to the fourth minus 2 over Q. And again, this must actually be the Galois closure. Not only is it a Galois extension of Q containing Q adjoin the fourth root of 2, but there's no smaller extension that could be in between these two just for degree reasons. This extension has degree 4. This extension has degree 8. Okay, so let's prove this. And there are two big steps. One is to just show that there exists some extension of F containing E that is Galois. So we're just going to find one Galois extension, and then we're going to take this one Galois extension and find a minimal one using it. Okay, so E over F is a finite extension. So it's generated by finitely many algebraic elements over F. So E is F adjoin theta 1 up through theta n. Each one of these theta i's has some minimal polynomial over F. E over F is a separable extension, so each one of these minimal polynomials is separable over F. Okay, if you take the splitting field of any one of those polynomials over f, you get a Galois extension of f. And if you take the splitting field of the minimal polynomial of theta I over f, certainly that's a Galois extension of f that contains theta I. So let's do this for every one of these theta 1 up through theta n. We get these n different, maybe. We get these n different extensions, or we get these n extensions, each of which is Galois over f. Maybe some of them are the same, but there's at most n different extensions. And you can take the composite of all of them. We've seen that the composite of Galois extensions is Galois. So we can take the composite 2 at a time, or we can convince yourself that if you take the composite of finitely many Galois extensions over f, you get a Galois extension over f. Okay, so here we're really using this fact that composites of Galois extensions are Galois. So that gives us one Galois extension of f containing E. But maybe this one isn't minimal in the sense that it contains all these other ones. So maybe there's some other Galois extension of f containing E. Well, we have this one, we have this other one. If we take their intersection, then we get a smaller Galois extension of f containing E. The main idea is that the intersection of Galois extensions is Galois. So the intersection of all of the Galois extensions of f containing E is a Galois extension of f containing E. And this intersection of all of them has to be the minimal one, because if there was any other Galois extension of f containing E that wasn't contained in this intersection, there would be a problem because it would be part of the intersection. Okay, so this intersection of all the Galois extensions of f containing E, that is this minimal Galois extension K. Okay, so I'm going to pause and erase, and I'll talk about one situation where it's kind of nice to describe what the Galois closure is. Let's end this video by describing one situation where it's easy to see what the Galois closure is. Remember, an extension K over F is a simple extension if there exists an element theta in K such that K is the field generated over F by theta. In this case, we call theta a primitive element for this extension K over F. Okay, so in this situation, if K equals F adjoint theta, if this is a finite separable extension, meaning, okay, the minimal polynomial of, so theta is algebraic, and the minimal polynomial of alpha over F is separable, then what is the Galois closure of K over F? It is the splitting field over F of this minimal polynomial. Why? Well, the minimal polynomial is an irreducible polynomial in F bracket X that has a root in K. And if you have a Galois extension of F that contains theta, it contains a root of this minimal polynomial. In a Galois extension, if an irreducible polynomial in F bracket X has one root in K, then all of its roots have to be in K. So certainly any Galois extension of F containing F adjoint theta has to contain all of the roots of this minimal polynomial. So it has to contain the splitting field of this minimal polynomial. But the splitting field itself is a Galois extension of F containing F adjoint theta. So it is the Galois closure of F adjoint theta over F. Okay, so when we're dealing with simple extensions and we have a primitive element that we can write down, it's easy to see how to compute the Galois closure. So in the next video, we'll talk more about simple extensions and primitive elements.